What if, at this very moment, there is another world almost identical to our own? A planet with blue oceans, white clouds drifting across its sky, continents shaped by billions of years of geology, and perhaps even civilizations looking up into their night sky, asking the exact same question we ask today: where is everyone else? For centuries, humanity believed that Earth might be unique. Then astronomy changed forever. We discovered thousands of planets orbiting distant stars. Suddenly, the universe no longer looked empty. It looked crowded. And yet, despite all of our incredible technology, despite giant observatories on mountaintops, despite telescopes floating in space, despite machines capable of looking back more than 13 billion years into cosmic history, we still haven't seen another Earth. Not one. Why? How can we observe galaxies billions of light years away, witness black holes colliding across the universe, and study the atmosphere of distant planets, yet remain unable to capture a clear image of a world like our own? The answer is far more surprising than most people imagine. Because finding another Earth isn't simply difficult. It may be one of the hardest scientific challenges humanity has ever attempted. Tonight, we're going to travel across the universe to understand why. We'll discover how astronomers search for invisible worlds, why most planets are found without ever being seen, how modern telescopes are reaching the limits of physics itself, and whether there may come a day when humanity finally gazes upon another blue world, orbiting another distant sun, or whether that moment may forever remain beyond our reach. Our story begins with a simple realization: the universe is unimaginably large. The observable universe stretches roughly 93 billion light-years across. Within it are hundreds of billions of galaxies. Each galaxy contains hundreds of billions of stars, and many of those stars orbit planets. For most of human history, however, we had absolutely no evidence that planets existed anywhere except around our own sun. It wasn't because they weren't there. It was because they were almost impossible to detect. Imagine standing thousands of kilometers away from a lighthouse. Now imagine trying to spot a tiny mosquito flying only a few centimeters away from the lamp itself. You wouldn't see the mosquito. The lighthouse would completely overwhelm your vision. This is exactly the problem astronomers face. Stars are unimaginably bright. Planets are incredibly dim. Earth, for example, reflects only a tiny fraction of the sunlight that reaches it. If an alien civilization were observing our solar system from dozens of light years away, our planet would be billions of times fainter than the sun. To them, Earth wouldn't appear as a blue marble. It would disappear inside the overwhelming glare of its parent star. This single problem has shaped the entire history of exoplanet science. Astronomers couldn't simply point a telescope toward another star and photograph its planets. Instead, they had to become detectives. Rather than looking for planets directly, they searched for the tiny clues planets leave behind. The first successful breakthrough came in the 1990s. Scientists realized that although a planet is much smaller than its star, gravity works both ways. When a planet orbits a star, the star doesn't remain perfectly still. Instead, both objects orbit around their common center of mass. The motion is tiny, sometimes only a few meters per second. But modern instruments are astonishingly precise. By studying subtle shifts in starlight, astronomers could detect these tiny movements. This technique became known as the radial velocity method. It revolutionized astronomy. For the first time in history, planets beyond our solar system were no longer theoretical. They became measurable. But there was a catch. The easiest planets to detect were not worlds like Earth. They were enormous. Massive gas giants, often larger than Jupiter, orbiting incredibly close to their stars. These planets tugged strongly on their suns, making them much easier to find. The universe suddenly seemed filled with strange worlds. Hot Jupiters. Gas giants orbiting so close to their stars that their years lasted only a few days. Some had temperatures hotter than molten lava. Others were so close that their atmospheres were literally being stripped away into space. None of them resembled Earth. Then came another revolution. Instead of measuring a star's motion, astronomers watched for something even smaller, a tiny dip in brightness. Imagine watching a powerful floodlight from many kilometers away. If a boat flew directly across it, the light would dim ever so slightly. The same thing happens when a planet crosses in front of its star. This event is called a transit. Whenever a planet passes between its star and our telescopes, it blocks a tiny fraction of the starlight, usually less than 1%, sometimes far less. For an Earth-sized planet crossing a Sun-like star, the brightness decreases by less than 1/100th of 1%. Detecting such a tiny change requires extraordinary precision. This challenge led to one of NASA's most successful missions ever launched, the Kepler Space Telescope. Kepler did something beautifully simple. Instead of scanning the entire sky, it stared continuously at more than 150,000 stars. Day after day, month after month, year after year, waiting. Most stars never changed, but occasionally, a tiny dip appeared, then another, always separated by exactly the same amount of time. Nature was revealing a hidden clockwork. A planet had been discovered. Kepler completely transformed our understanding of the galaxy. Before its launch, scientists expected planets might be common. After Kepler, they knew. Virtually every star in the Milky Way probably has planets. Some have one, others have dozens. Many planetary systems look nothing like our own. Some contain tightly packed super-Earths. Others have giant planets orbiting incredibly close to their stars. Some worlds may be made largely of water. Others may rain molten glass. Still others could possess skies permanently covered in clouds made from vaporized metals. The universe turned out to be far stranger than anyone expected. And yet, despite thousands upon thousands of discoveries, we still had not actually seen another Earth. Because Kepler never photographed these planets, it merely observed their shadows. Imagine discovering an entire zoo by watching silhouettes move behind a curtain. You could estimate their sizes, their movements, perhaps even their behavior, but you would never actually see the animals themselves. That is essentially what astronomers have been doing for decades. Even our greatest discoveries often come from indirect evidence. And this brings us to perhaps the biggest misconception in modern astronomy. When people hear that scientists have discovered 5,000 exoplanets, many imagine 5,000 photographs. Nothing could be further from reality. For the overwhelming majority of known exoplanets, we have no detailed image whatsoever. Not because our telescopes are poor, but because physics itself is working against us. Imagine shrinking a solar system until the Earth and the Sun fit inside a single coin. Now place that coin thousands of kilometers away. Could you distinguish the tiny Earth from the brilliant Sun? Even with the most advanced optical instruments ever constructed? Probably not. That is the scale of the challenge astronomers face every single night. But even if we cannot directly see another Earth, we are not completely blind. Modern astronomy has developed one more powerful technique, one that feels almost like science fiction. Instead of taking pictures of distant planets, scientists can now study their atmospheres. They do this using starlight. When a planet passes in front of its star, a tiny fraction of that starlight filters through the planet's atmosphere before reaching our telescopes. And in that faint, distorted light, something extraordinary is hidden. A chemical fingerprint. Different molecules absorb light at specific wavelengths. Water vapor, carbon dioxide, methane, oxygen. Each one leaves behind a signature like a barcode written into the light itself. By carefully analyzing these patterns, astronomers can begin to reconstruct the invisible layers surrounding distant worlds. This technique has already revealed atmospheres of gas giants many light years away. Some are scorching hot, others contain strange metallic clouds. A few appear to have weather patterns more violent than any storm ever recorded in our solar system. But when scientists turn this method towards smaller, Earth-like planets, everything becomes dramatically harder. Because the signal is so weak, so fragile, it is like trying to read a single drop of ink dissolved into an entire ocean. This is where the James Webb Space Telescope enters the story. Floating far beyond Earth, orbiting a stable gravitational point, it is one of the most sensitive instruments ever built by humanity. James Webb was not designed to find another Earth directly. Instead, it was designed to study the atmospheres of worlds that might one day resemble Earth. And even Webb has limits. For Earth-sized planets orbiting sun-like stars, the signal is often too faint to clearly detect atmospheric biosignatures. We can sometimes detect larger super-Earths, or planets orbiting small red dwarf stars. but a true Earth twin, a planet nearly identical to ours in size, temperature, and atmosphere, remains just beyond reach for now. And this brings us to a fundamental truth that is rarely spoken about clearly. The reason we haven't seen another Earth is not because it doesn't exist. It is because our current technology is still not powerful enough to isolate it from the overwhelming brightness of its star. To directly image such a planet, astronomers would need to block out the star's light almost perfectly, while preserving the faint reflection from the planet beside it. This is similar to trying to observe a firefly flying right next to a spotlight from thousands of kilometers away. And yet, humanity is already building the next generation of tools designed to solve this problem. One of the most promising concepts is called a star shade. It is exactly what it sounds like, a giant structure placed in space, shaped to block starlight with extreme precision, allowing telescopes behind it to capture faint orbiting planets directly. Another approach involves extremely large ground-based telescopes, with mirrors stretching tens of meters across, designed to resolve finer and finer details in distant star systems. Projects like the Extremely Large Telescope are pushing optical engineering to its limits. But even these might not be enough to guarantee a clear image of another Earth-like world, orbiting a sun-like star, because at some point we collide with a hard boundary, not a technological one, a physical one: diffraction. Light itself has limits. No matter how perfect your telescope is, there is always a smallest possible detail you can resolve, determined by the size of your instrument and the wavelength of light. To go beyond that, you must build something impossibly large, or find entirely new methods of observation. This is why some scientists believe that the first truly Earth-like planet we see may not come from a photograph at all. It may come from data, from indirect signatures, from atmospheric chemistry that suggests the presence of oceans, continents, and perhaps even life. But even that raises another question. If we do find a true Earth twin, how would we know? What would be enough to convince us that a distant world is not just similar to Earth, but truly alive? On Earth, life has transformed our atmosphere over billions of years. Oxygen is unstable in large quantities. It should not exist in a planet's atmosphere unless something is continuously producing it. On our world, that something is biology. But interpreting such signals from light years away is extremely dangerous, because nature is deceptive. Processes that have nothing to do with life can sometimes mimic biological signatures. A planet might appear alive when it is not, or worse, we might miss a living world entirely because its chemistry does not match our expectations. So even if we eventually find a planet that looks like Earth in every measurable way, there will always be uncertainty. And that uncertainty leads to one of the most profound questions in science. Are we searching for Earth? Or are we searching for something we already understand too narrowly? As we push deeper into the cosmos, we begin to realize something unsettling. The universe may be filled with Earth-like worlds, but seeing them directly may remain further out of reach with conventional telescopes. Not because they are hidden, but because the distance between stars is not just a gap in space. It is a barrier built into the nature of light itself. And yet, despite these limitations, humanity continues to push forward. Because every generation of astronomers has said the same thing: we are close, closer than ever before. And perhaps, somewhere in the near future, a new telescope will quietly observe a distant star. And for the first time in history, a faint, pale blue dot will appear beside it. Not a simulation, not an inference, but a real image, a second Earth. And when that moment arrives, it will not just change astronomy. It will change everything we believe about our place in the universe. But until then, we are left with a universe full of questions, and a single world that we know for certain is alive, ours. And maybe, just maybe, not alone.